back to proximate analysis, plugging along, and today we're going to talk about protein analysis, so which will be the subject of next week's lab. A little bit of a review, very slight review from your food chemistry knowledge. Which of the following absorb light in the UV region? Yeah, A. Only A?
C. A and C.
A and C. So tryptophan and tyrosine and phenylamine are all aromatic amino acids. So, and tryptophan in particular has the highest molar extinction or absorptivity. So it absorbs the most out of the other, out of the three aromatic at the UV range 280 to be specific, 280 nanometer. So these are your aromatic amino acid, tyrosine, tryptophan, and phenylamine. And they absorb in the 280 region. And every protein, no matter what its source is, has aromatic amino acids in their composition to a certain extent. And that's why all proteins absorb at 280. Okay? What about peptide bond? What is true about the peptide bond? Riley?
A and C. Oh, wait, notice A.
Just A, Riley. You redeemed yourself. Okay, yes. It's a covalent bond, but between the amine group, between the carboxyl group and the amine group of another amino acid. So the carboxyl group of one amino acid bonds with the amine group of the next amino acid. This is a peptide bond. Why do we care? Because peptide bonds absorb light at 220. So 220, 216. Alex, you can come over if you like. That's okay. Okay. So it absorbs light at 220. It can absorb light in the range of 214 to 222 nanometer. And why do we care about peptide bond as well? Because they act as, they can reduce and take part in a reaction that we will utilize for determining a protein content. And that is in the BCA assay that we will talk about later. Bicynchroninic acid assay, which is a research assay that we use in lab for protein solutions that can be clear. If they are clear, then we can use absorption spectroscopy to determine concentration. And the BCA is a method that is based on absorption, and we will talk about it later. And peptide bond plays a role in that reaction. Okay, that's it for your food chemistry background. Diving into analysis, why is it important to analyze protein content? Very obvious reason. One,
Nutrition.
for nutrition labeling, because protein is on the nutrition label itself. What else can you think of?
Helps determine carbohydrate content later on.
Sure. So we need the composition to complete the composition analysis. So again, this is for nutrition label. Anything else? There is a list of things. Yes, Lauren.
It might be important to know the protein content for your product, like if you're using a flour.
Yes. So for quality control or quality assessment of your product, Megan, you had something to say.
I was just going to say, like, protein content in milk.
Protein content in milk, which is part of its standard of identity. Okay, another thing, for researchers that work in our lab in particular, So when you're fractionating protein and you're isolating and you're collecting fractions to do other measurements, you want to determine how much protein you have collected. That will help you determine purity and determine how much you need out of this fraction for another analysis. And also, for example, if you're a company producing ingredients and you're producing a protein concentrate versus a protein isolate ingredient, the difference between the labeling of a concentrate and isolate is how much protein they have. So a concentrate, for example, whey protein concentrate it can have 30 to 80% protein. It will be labeled as concentrate. But if it has 90% protein or higher, it's labeled as isolate. Another one is when we are looking at functional properties of proteins, you want to determine the protein concentration. So for example, if you are measuring emulsification capacity, which you will be doing in chemical reaction, for example, so you want to determine how much oil can be emulsified by 1 gram of protein. Because emulsification capacity, the unit is amount of oil emulsified by 1 gram of protein. So in order to determine the functional properties, you need to know how much protein you have in solution. So when you add the oil, then you can convert to that unit for the emulsification capacity. Same for other functional properties. If you're doing gelation, you need to know. If you're doing protein solubility, you need to know protein concentration. Biological activity, because for example, enzymes are proteins. So if you want to determine enzymes and enzyme inhibitors as well. So if you want to determine trypsin inhibitor amount that is present or how much it's active in a soy product, which soy is natively high in trypsin inhibitor, and you should process the soy product to inhibit 90% of the activity of trypsin inhibitor. So that is why we call it biological activity for enzymes and enzymes inhibitors, because both are proteins. Okay, so there are many methods to determine proteins, but the official methods of analyses are Kjeldahl and Dumas. Both methods you will learn next week in lab, and both methods can be used for nutritional labeling. So there are primary methods of analysis, there are official methods of analysis, and both can be used to calibrate, either one of them can be used to calibrate IR and mid-IR instrumentation for online and quality assurance quick measurements. So there are primary methods of analysis, and both are based on determination of nitrogen content, and then which can then be converted to protein content, and which brings me to here. We'll start with the Kjeldahl principle. The Kjeldahl principle, basically we're measuring nitrogen by an analytical method that involves three major steps: digestion, neutralization, and distillation. It is one step, it's done together, and titration is your third step. So when I ask you, provide me the principle of Kjeldahl, you have to state that there is a digestion with an acid. We'll go over that in detail. And then neutralization with a base, and distillation, and then titration with an acid. And we'll go over those steps in a minute there. All of these steps will eventually lead to quantitating nitrogen. And then from there, nitrogen is converted to percent protein. Why is that? Because there is a considerably amount of nitrogen and protein coming from the amino groups in your amino acids. And on average, you have about 16% nitrogen in a given protein. Because you have a 16% nitrogen, you can convert percentage of nitrogen to percent protein by a conversion factor, which is 100 over 16. 16 is the percentage of nitrogen. It gives you the average conversion factor, which you use to multiply by percent nitrogen. Now, different proteins might have different percentage of nitrogen. Why is that? Because, do you know what amino acids are basic?
Shoot.
What, you raised your hand. What did you want to say?
Isn't asparagine? No, hold on. Lysine.
Lysine is a basic amino acid. Thank you. So we do have basic amino acid: lysine, arginine, and histidine. These are 3 basic amino acids. And by basic amino acid, they are basic. Ted, are you with us? Okay. Thank you.
Basic because they have an amine group on the chain.
You are with us. Good. So, so you have an additional amine group in basic amino acid. So you have more nitrogen. So if you have higher percentage of these basic amino acid, then you end up having a protein with higher percentage nitrogen. And if that happens, then here it's not 16, it could be 18, it could be 20, whatever it is. So your conversion factor will be less than 6.25. So for example, wheat has relatively high amount of basic amino acids. So for wheat products, the conversion factor is 5.6 or 5.8, Rachel. Okay, so it's somewhere along these lines. So you would have higher percentage of amino acids. For milk, for example, the opposite. You have less percentage of basic amino acids, so your conversion factor is higher because your average percent of nitrogen in dairy protein is less than 60%. So the conversion factor for dairy is 6.38. So in lab next week, if you have a wheat-based product, you will use a conversion factor, I believe it's 5.7. And then for dairy, if you have cheese, you will use a conversion factor of 6.38. But if you have almonds, for example, you would use the general factor, which is the 6.25. When you're not given a factor, yes?
How does this work with something like pure D? Has nitrates or nitrites added?
That brings me to the next thing I was going to talk about, which is crude protein. So in crude protein, it's called crude protein. Why is called crude protein, Ted? So it includes nitrogen from other sources than protein sources. So if you have nitrates and if you have nucleic acid, or if you have high amount of vitamins or phospholipids, these have some nitrogen content in them. So this will actually increase the amount of protein that you're calculating. So we call it crude because it's not the exact amount of protein. Most of the nitrogen in your sample is coming from the protein, but some nitrogen is coming from other sources, and hence the crude protein. So if you have a cured meat, well, unfortunately, you are going to detect those nitrogen in your sample, and you have higher protein content than what you actually have. Okay. So I really love Keldal. So I hope you're going to enjoy doing it in lab next week. It's a very dangerous method. And I did cause trouble when I was a graduate student. I'll tell you the story in a minute. I always tend to have hazards in the lab. I don't know why. I'm not a very safe person. But anyway, it's a fun method and it's a lengthy method. So it involves your main steps: digestion, distillation, and titration. In distillation, you have a neutralization step embedded in distillation. So the first step of Keldal is your food sample is digested with concentrated sulfuric acid. So the sulfuric acid is about 98% So it's really concentrated, so it's going to burn and digest your sample. So as soon as you put your food with the concentrated H2SO4, it's going to start turning black, burning, and then when you put it on a heating block, it starts fuming. So what comes out are vapors. So these vapors are CO2, H2O, and SO2. However, the nitrogen or the amine groups that are in the protein gets fixed. This is an important term to remember, fixed as ammonium sulfate. Notice this is in red because this is what you're following. You're following the nitrogen in this reaction. So the amine groups get fixed as ammonium sulfate. And that's what we want. We want to fix our nitrogen and get rid of everything else. So everything else will be gone as fumes. So the reaction requires concentrated acid and requires heat, and there is a catalyst. So the catalyst, it's basically a combination of different salts. What they do is basically speed up digestion, otherwise it will take much longer than what it actually takes. And they increase the boiling point of the acid, which is very important because you don't want the acid to boil off. You want it to stay and digest your food and be efficient at it. So the catalyst increase the boiling point of your acid. So from there, the next step is the neutralization/distillation. The neutralization/distillation is basically you have acid in the system or remaining acid in the system. You neutralize with NaOH, and some of the NaOH will react with the ammonium sulfate. So the ammonium sulfate will react with the NaOH, gives you ammonia gas and salt and water. Okay, so now your nitrogen is in the form of ammonia gas, hence the distillation. So ammonia and water will be vapors, and then they will be distilled into a container that has boric acid and an indicator. The indicator is methyl red in this case. So boric acid and methyl red will give you red color. As the ammonia gets into your collecting flask, or what's condensing into that flask that has boric acid, when the ammonia gets into the boric acid, in the presence of the indicator, you start seeing the color changes from pink, red, to yellow. The methyl red is yellow in a basic situation. So now you fixed your nitrogen as ammonium borate. So now your nitrogen is in the form of ammonium borate. So 1 molecule of ammonium to 1 molecule of ammonium borate. This is very important that they are equimolar. The final step is you titrate the borate back to boric acid. Right? So, and the reaction is also equimolar. Number of moles of borate would be at equilibrium equal number of moles of hydrogen ions from HCl, from the acid. So number of moles of borate equal number of moles of the acid. And so once we neutralize, that means when we bring back the boric acid and the color changes back to pink, because now we're back to acid, at that point, number of moles we used of acid is equivalent to the number of moles of ammonia present in the sample, because we have 1-to-1 ratio ammonium ion to borate ion, and 1-to-1 molar ratio of hydrogen from the acid to the borate. So this way we can deduce, we'll go through the calculations in a minute, using the volume of the HCl used and the molarity of the HCl used, we can use this data to quantitate or determine how much ammonium or nitrogen we had in our sample. very simple, but it is a lengthy process. Any questions about this? Okay, we'll go over it again in lab, step by step, with visual and with application. But here's what you're going to be seeing in the lab. You have the digestion block. And that's where we're going to digest the sample in tubes like that. We're going to put the sample, the catalyst, the acid, and put it in a heating block. And this is an exhaust system. That means fumes will be captured. You don't want to inhale any CO2 and SO2 and H2O, or even acid fumes. So you don't want to inhale any of that. So it's all closed system under the hood. So basically that's the digestion happening with the heater, and then what happens is it will get the ammonia, and the ammonia in the form of ammonium sulfate, it will react with NaOH, give you ammonia. Ammonia will condense into your flask, turn the pink to yellow, and then you titrate with acid back to pink. And this is actually the distillation unit that you will be working with in the lab. Here's your flask that had your digested sample. When it's digested completely, it will be clear because all of the organic matter is burned off, and then ammonia is in the form, or nitrogen is the form of ammonium sulfate. Now, why is it blue? It will be a clear, nice blue color. Where is the blue coming from?
Copper.
The copper from the catalyst. So this will give you a bluish color, but it has to be clear. If it has anything not digested, it will have some brown still. That means you will have incomplete digestion. You might not be able to quantitate the nitrogen accurately. And then we'll add the NaOH in this flask, and then we heat by steam, and then ammonia will evaporate along with water vapor, gets condensed into the flask that contains boric acid and the indicator. And that gets titrated. Oh, this is just illustrating the reaction of following the nitrogen, basically, from the polypeptide. Then it becomes fixed as ammonium sulfate, then reacts with NaOH to give you ammonia, and then reacts with boric acid to give you ammonium borate. So we're basically always following the nitrogen. And here's the very old system that I personally worked on some 20-some years ago. And here it's one unit where you can do digestion down here. These are the heating blocks, and we used round bottom flask, long neck, that we connect to the exhaust system. And then after digestion, we do the neutralization and distillation on top here, and then in the back, we put the collecting flask with the boric acid. And then here's where I one time forgot to turn on the exhaust, and then all the fumes spread out in the lab and the hallway. And then I was coming out to check on it, and we had a very tall professor at the time. And all I saw is a head walking, and then under him was clouds, and he was just waving at me and yelling at me. So what did you do? We're going to die out here. It's like, I'm so sorry, I just forgot to turn on the fumes, the exhaust system. But hopefully we have it contained in the lab, so that you don't smell or inhale any of the fumes. Okay. Finally, after titration, we collect the amount of HCl that we use to titrate ammonium borate back to boric acid, and that volume of HCl is used in an equation to determine percent nitrogen, and then we convert it to percent protein using the conversion factor. Now, how does the calculation work? Let me walk you through the calculation, because this type of calculation, it will come back to you in other labs and other calculations, for example, titratable acidity. So let's walk through what are we after? We're after percent nitrogen, and percent nitrogen is weight by weight. So I'm after getting mass of nitrogen per the amount of sample I've used. So I'm looking for mass. Mass of nitrogen is what I'm after. Okay. I told you originally that number of moles of nitrogen is going to be equal number of moles of borate ion is going to be equal number of moles of HCl. Okay, that's at the end, at equilibrium. So the number of moles of nitrogen will be equal to number of moles of borate equal the number of moles of HCl. We can get the number of moles of HCl because we know the molarity and we are going to know the volume. So this is easy. We don't care about this. The number of moles of nitrogen is equal what? Number of moles equals mass over molecular weight. Okay? I'm searching for mass of nitrogen. So mass of nitrogen in grams equal number of moles times molecular weight. Are you following? Good. So number of moles of HCl equals what? Molarity times volume. Because molarity equals number of moles over volume. Right? And molarity of HCl equal normality. Why? Do you remember why molarity equal normality?
Only has one hydrogen.
Only have one hydrogen. Thank you very much. So number of moles equals normality times volume as well. Okay, so since number of moles of HCl equals number of moles of nitrogen, I can put it here. I can replace that by HCl information. So I'm going to say mass equal number of moles, which is normality times volume times molecular weight. Okay, now I want percentage. So percentage equals normality times volume of HCl times molecular weight over the weight of the sample times 100 and that is your equation. And we say corrected because we always run a blank. You will be running a blank along with your sample because you want to correct for any nitrogen that comes from any reagent that you have used. So the corrected volume is basically the volume of the sample minus volume of the blank. And that's what you're going to be doing. Okay, so that is how we derived this equation. Any questions about how that equation came to be? All right then, let's do some calculations. Bring that piece of paper that you were working on last time with the fat. So you have sample 1 and sample 2, meaning do the calculation for each sample separately all the way to the end. Yes, Riley?
Which molecular weight is it?
Oh, molecular weight of nitrogen, which is 14. So here it is mass of nitrogen with number of moles of nitrogen times the molecular weight of nitrogen. Anybody with an answer for percent protein? Nope, not yet. Anybody with a value? Do you have something?
For the wet basis, not just dry wet.
Not dry? It would be a dry. Huh? You are calculating on dry basis because it's a dehydrated.
Okay.
So your value is on a dry basis, right?
Okay.
Yeah, what is your value?
For the first sample, I have 19.8.
0.8?
Yeah. And then I have 20%.
What did you use as your conversion factor?
5.7.
Okay, so maybe you did some rounding there?
Yeah.
You rounded, so you divided 100 by 17.5?
Yes.
And you got...
I got 5.7. 1/4 is longer.
Oh, okay. Yeah, well, my calculation, I just multiplied by 100 divided by 17.5, so that's why I'm a little off in few decimal points. But yes, so basically, here we go. You just apply the equation. I don't expect you to derive the equation, but the reason I derive the equation over there is for you to understand how we got to this equation. It's really important that you know how we got to this equation. I did not put all the units, but I appreciate it when you have it in your lab report to to put units. So percent nitrogen equals normality of HCl, so we're going to have that in moles per liter. And then you multiply that by the volume, and the volume is volume of sample minus volume of blank. This is in milliliter. Because normality is in liter, so you really have to correct. So you divide by 1,000. So you are converting the milliliters to liters so that you can cancel the units. So this is important. So this is here milliliter. And then you multiply, well, you divide by the weight of the sample, which is in grams. And then here you multiply by the molecular weight of nitrogen, which is grams per mole. So now everything will cancel, right? And then you multiply by 100. So all of the units will cancel. Then you get a percentage. So here you have 22 minus 0.2, which is the blank. So 22 milliliter minus 0.2 milliliter. And the normality is 0.1. And the weight of the sample for the first sample, 1.015. So you have everything to determine percent nitrogen. You get the percent nitrogen and you multiply by the factor. And the factor is 100 divided by the nitrogen percentage. You'll get the first percent crude protein for sample 1. You do the same for sample 2, and you get your 2 replications. From there, you average. You get the average. And now this is on dry basis. How do you convert to wet basis? What's the equation of converting dry to wet? So you have 19.7 grams of protein in 100 grams dry matter. You want to determine that amount on wet basis, right? So how much is in your original dry matter, which is 100 minus 8. Okay, so your moisture is 8. So basically 90.7 times 100 minus 8 over 100 will give you the percentage on wet basis. And always wet basis is smaller than dry basis. Then you know that you got it right. Oops, sorry. Just make sure you have that. Okay. Good. We all got that? Any questions? Yes, Zach?
Are these the calculations we'll be doing for the lab?
Huh?
Are these the exact calculations we'll be using for the lab?
Yes. For your sample, but every sample will have a different conversion factor for the protein. Okay. All right. So next, let's talk a little bit about the DUMAS, which is a nitrogen combustion method. That means we are combusting the sample at high temperature. Then we are determining the amount of nitrogen gas using a thermal conductivity detector. So that's why it's called nitrogen combustion, because we are combusting the sample at really high temperature. So this is the picture of the instrument that you will be using in the lab. It's the LECO. The LECO is the make of it, the company make, and the DUMAS is the official name of the method. So what we do, what you see here, you have here the compartment where you put in your samples. You weigh your samples in capsules. We call them capsules. There can be either gel capsule or tin capsules. You weigh a small amount of sample, about 0.1 gram or 0.1 to 0.2 grams, depending. And then you insert your capsule in little holes, and then the capsules get dropped into the combustion chamber, where it's really hot at about 950 degrees C. So it's really hot. Everything combusts into gases. So then they get diverted to a filter and also a scrubber for moisture, and then they go to a ballast. The gases are directed to a ballast, a compartment in the back of the instrument, and oxygen is flushed, that everything is homogenized in there. And after they go there, they get directed to a copper finger where they get reduced. All of your NO2 and get reduced to nitrogen gas. And actually, before they get to the copper, CO2 and H2O get scrubbed off. They get collected here, and NO2 makes it to the copper, and the copper reduces the NO2 or NO whatever, NOx, into nitrogen gas, and the nitrogen gas gets taken by helium. Like helium is your carrier gas, and then floats onto your thermal conductivity cell, where the change in conductivity is converted to the concentration of nitrogen. Because it will be measuring conductivity when only helium is passing, and when nitrogen pass, you have a change in conductivity, and then you convert that, or the system, the software converts that into concentration of nitrogen. Typically, the analysis takes 4 minutes. However, we really have an old, cranky system. Because it's old, now the analysis takes about 8 to 10 minutes, so it's a little longer. But soon we're going to get a new unit, and really the analysis time would not exceed 4 minutes. So it's quick, rapid. We have a carousel. That means you can insert many samples at one time. You can have many samples already weighed and placed in the carousel, and one at a time get combusted. So you can measure a lot of samples quicker than doing the cowbell. So this is another schematic where oxygen gas is used. Here is illustrating that compressed CO2 and oxygen used for the combustion. We have a carrier nitrogen gas, we have scrubbers, samples get combusted and then they are scrubbed off, and then they are reduced into nitrogen gas. And then sometimes you have kind of a chromatography column. If you only have a scrubber for liquid, for example, then you are separating all the other gases using chromatography column, and then you have a thermal conductivity detector. But in our unit, we have scrubbers, multiple scrubbers, to get rid of all of the other gases and only allow nitrogen to go to your thermal conductivity cell detector. So if we want to compare and contrast Kaldal and Dumas, so principle, they have a similar principle in the sense that we are after determining nitrogen amount and then converting it to protein. So both are based on determining nitrogen, but one is instrument based and the other one is what chemistry based. So that's the difference in instrumentation. One is automated. You just weigh your sample, put it in there, and it does everything for you. However, the instrument requires maintenance. It's really pain to maintain it. It's highly expensive to start with, and then maintenance is expensive as well. But when it works, it saves you a lot of time. So in terms of time, it's more efficient. It does require calibration, where the Kaldal does not require calibration. So you'll see that with the nitrogen analyzer Dumas method, we have to calibrate to make sure that your nitrogen content fits a certain standard curve so that we can do the calculations. It is very safe in terms of not using corrosive chemicals, no NOH, no concentrated sulfuric acid. So it's much safer to use it. In terms of application, there are kind of common. You can use either Kaldal or Dumas. They're both official. Whatever is available, whatever is more time efficient for you and cost, you go with. We'll talk more about it in more detail in lab, obviously, when you're actually running your samples. But that's it. I'm going to stop here and then we can continue on Friday.